component. We have compressor, we have blower. Okay, the compressor, the function is to cool the air, and then the blower will blow the air into your room. Okay, so there are many systems that you can see in your house. There is an oven, there is a vacuum, there is a mobile robot, ATM machine. Okay, all this is a system where we can see in that system there are a few devices or components that add together. All right, so then we have a control system. Okay, we have a control system or control method. Okay, so here the system that we have identified, okay, any system that you have identified, sometimes the performance is not as what we want. Okay, it may produce, for example, an aircon. It may produce cold air. For example, you have set 24 degrees Celsius for your room, but that temperature may not 24. What you feel in the room may not provide 24 degrees Celsius. Okay, it may give you 26 degrees Celsius. Okay, it may give you only 18 degrees Celsius. Okay, so in this example, in this aircon system, we require a control system that allow us to control so that it will be able to give us the desired output. Okay, so it is actually a system. Okay, it's a system, but it not perform as what we want. So therefore, we need to add another component, which is called as a controller, in order to help the system able to provide the desired output. Okay, the desired output as what we want. Okay, so you may have a conventional system. Okay, for example, toaster. Okay, so your toaster may not give your desired output. Then okay, you say you need to add a control system so that it will have the toaster provide an output as what you want. Okay, all right. So normally, okay. Okay, so in order to control a system, first we need to understand the system. Okay, you need to understand the flow of the system. You need to know the components in the system. What are the components? For example, aircon system. There is compressor. There is a blower. Okay, there is also refrigerant. So we need to understand the process of that system, the flow from the input and the process, and then we get the output. So by understanding the system, okay, we will be able to control the system. Okay, because we know that there are many components in a system. Okay, so we need to select appropriate components that allow us to control the system, which will eventually allow the system to give us the desired output. Okay, so when we talk about aircon, we need to understand the process of aircon. If you talk about a mobile robot, we need to understand how mobile robot work. If we want to control ATM, we need to understand the process and also what are the components in the ATM system. Okay, all right. Okay, next. Okay, so when we analyze a system from a control viewpoint, okay, normally we want to see a block diagram. Okay, in control, we we normally we would like to see a system in terms of block diagram, because by viewing a system using a block diagram, we can see what are the components. Okay, we can understand the flow from the input. Then you can see the flow from the input to the actuator, and then it will actuate the system, and then we provide the output. Okay, so in control system, normally we represent a system using a block diagram. In a block diagram system, you can see here there is a block. Okay, a block. Okay, so that block normally represent the system. Okay, when we say it represent the system, actually we have a model that represent the behavior of the system. Okay, sometimes we call the model as a transfer function. Okay, you may heard later transfer function. Okay, transfer function is actually a mathematical relationship that relates between the input to the system. Okay, there's an input arrow to the system. Okay, so we apply the input to the system, and then it will actuate the system. Then it will provide the output of the system. Okay, for this kind of block, for this kind of system where you see there is only one input and one output. Okay, so this one we consider as a, let me just use text there, it's easier. Okay, we consider that to be as a seesaw system. Seesaw system. Seesaw represent as single input, single output. Okay, so single input, single output, we call that as a seesaw system, where a system only has one input and one output. Okay, but normally we know that when there are many components, many devices in the system, meaning we can the system able to receive many inputs and also able to provide many output. Okay, for example, your handphone. Okay, your handphone has many functions there. You can use your handphone to call, to send SMS, to read email, to what else? To do calculation on calculator. Okay, so meaning there are many outputs that you can get from a handphone, and of course the input will also be many. Okay, so for that kind of system, we call that system as a MIMO. So it stands for multiple input, multiple output. Okay, so you can see a single input, single output system, SISO, or you may also see that your system is a MIMO system, multiple input and multiple output system. Okay, but when we're going to control a system, we would like to simplify the system. Okay, if your system is a MIMO system, normally one controller we only able to control one output. Okay, because if you're going to control many outputs based on one controller, then it's going to be a very complex controller. Okay, instead what we're going to do is we just focus on one output and one input, meaning we represent the system as a seesaw, so that the controller will become more simple. Okay, instead of using having a complex controller. Okay, a very good practice to have a simple controller dedicated to one function. Okay, so therefore you can see in here, in the block diagram here, you have input and output. Okay, one input and one output. Okay, other than that, you also have a control variable. Okay, sorry. Okay, Control variable. Okay, control variable is something that we know that the variable will affect the performance of the system. Okay, so we need to determine what is the control variable for this system, right? So that's why you need to understand the flow and the process and also the components in the system, so that you are able to you'll be able to identify what is the control variable for the system. Okay, last one is the disturbances. Okay, so disturbances is something is a parameter that that is we doesn't count this parameter when we control the system, but the disturbance is sometimes will affect the performance of the system. Okay, for example, you have an aircon system, okay, in your room, and then you set the temperature to 24 degrees Celsius, right? Then then someone accidentally opened the windows in that room. Okay, so the window, okay, is actually the disturbance to the system, because it allow heat from outside, and then it allow the heat from outside into the room, and then the heat will affect the performance of the aircon system. Okay, so that is the example of disturbance. Okay, so we normally if your system is a open loop controller, later I will introduce to open loop and closed loop. Okay, if your system is open loop controller, then the disturbance will affect the performance of the system. Okay, but if your system is in terms of closed loop controller, normally your controller will be able to compensate, be able to eliminate the effect of the disturbance. Right. Okay, next. Okay. All right. So where we can find the application of control engineering. Okay. So of course you can see we are learning in mechanical. So of course you can control. You can find the application of control engineering in mechanical system. Okay. For example, in a car. Okay. You'll be able to control the speed of the car. You'll be able to control the trajectory of the car, meaning you'll be able to allow the car, even nowadays we have autonomous car today. Okay, we allow, meaning the component, the system allow the car to be controlled autonomously, without intervention from human. And of course, a car is actually a combination of mechanical, electrical, okay, and mechatronic. Okay, so other than that, in chemical, we have a chemical plant where we need to control the pressure in the plant, chemical plant, the temperature. Okay, aero. Okay, you can see in a cockpit of aeroplane, there are many die, many monitor, which allow the pilot to control the performance of the aeroplane. Okay. Okay, civil. Okay. I'm not sure about the example of civil application, but example of a civil application is like vibration control, where we'll be able to control the vibration on a high-rise building. Okay, because the building will be vibrate due to the wind. Then you can apply the control application there in order to control the vibration. All right, and of course, non-engineering, but of course the controller is not control engineering, but for the non-engineering, there is also a control system in there. All right. So in control system, we have two strategy. Okay. Oh, two type of controller system that we can use in order to control any system. Okay, the first one, what we call as open loop control system, or also known as a feedback feed forward control system. Okay, open loop or feed forward control system. Okay, so open loop control system is actually it is one way process, one way controller. Okay, there is no loop. Okay, that's why the name is open loop, and because it's one way, we call it feed forward. Okay, as compared to the closed loop. Okay, closed loop, you can see there will be a loop from the output to the input, and this loop is also known as a feedback. Okay, so that's why the name is closed loop or feedback control system. Okay, this is an example of open loop or feed-forward control system, where it just consists of a process, a system, a plant. Okay, you apply your desired input, your setting. Okay, then the process will react to the input. Okay, and then it will provide the output. Okay, but we don't know whether the output is actual as what we set. Okay, for example, you have a aircon system in your room. Okay, you set at 24 degrees Celsius, but the aircon will react to your setting, meaning you will see you will hear the sound. Okay, and then you will hear the fan increasing. Okay, but you don't know whether the actual output is actually 24 degrees Celsius or not. Okay, because you don't have a thermometer to measure that. So meaning there is no feedback from the system telling the system that it is actually 24 degrees Celsius. Okay, so this is what we call as open loop control system. Okay, other example, toaster. Okay, if you have watched the video that I shared in the e-learning, the example is toaster. Okay, you put your bread into the toaster, and then the output, your desired output, is the color of your toast. Okay, so okay, so when you put your bread, you turn on the toaster, it will provide you a toast. Okay, it provide you a toast, but sorry. Okay, the toaster will provide you a toast, but but you don't know whether bukan you don't know lah. The system doesn't know whether the toast is as what you desire or not. Okay, so my suggestion is for you to watch the video so that you can see the explanation on the toast system. It's a very good video from I think MATLAB. Okay, to explain the example of open loop system. All right, as compared to a closed loop system, okay, you can see in a closed loop system, the system is more complex because there is additional component to that. Okay, instead of having just a plant there, okay, we add another component such as actuator. Okay, actuator is a component that allow us to control it. Okay, we're able to adjust the input to the actuator, then the actuator will actuate the system. Okay, and then we add sensor. Okay, the function of sensor here is to measure what is the actual output that provided by the system. Okay, so this is some sort of feedback. Okay, it will give a feedback from the system to the controller by comparing to the input. Okay, here you can see there is a this is a summation point. The function is to compare between the input and also the actual output. Okay, so here is what we call as error. Okay, meaning error here is the difference between the input and the actual output. Okay, so the error here will be used to the controller, meaning the controller will use the error information in order to provide the control signal. Okay, so here is what we call as control signal. Okay, so the type of control signal will depend on the type of actuator, meaning what are the type of signal that will be that is understand by your actuator. For example, one example of actuator is motor. Okay, so the motor, we control the motor using voltage. Okay, so meaning the controller need to calculate what is the suitable voltage to be the input to the motor, so that the motor will be able to actuate the system, the plant. Right? So you can see by having a feedback. Okay, sorry. Okay, sorry. Okay, that is the disturbance. Right. Okay. Okay. Again, closed loop system will have a more complex system compared to open loop system. All right. So this is a comparison between the open loop and closed loop system. Okay. First, we can see that from my explanation just now, you can see that an open loop system normally has a very simple and the controller is easy to design. Okay, the system is very simple. One example of open loop system is on-off system. Okay, we just on and off the system. All right. While for the closed loop system, we can see that the design is more complex. We need more components there. You need to add control. You need to add controller. You need to add actuator, and also need to add sensor. Okay. Second one, this is the disadvantage of open loop control system, meaning it's very sensitive to disturbance. Okay, meaning if there is disturbance to the system, all right, so the performance will become poor. Okay, the performance will be affected by the disturbance. Okay, because the system doesn't know there is disturbance. Okay, so the system just keep doing keep doing the function that has been designed for it. Okay, without knowing there is a disturbance to the system. Okay, so the performance will be deteriorated due to the disturbance. Right. As for the closed loop system, okay, we can say that closed loop system will be insensitive to the disturbance due to the feedback. Okay, meaning because we know the system know that the output is not reaching what we set yet. Okay, for example, for the aircon system, we set 24. Then it is a closed loop system, meaning there is a sensor, there is an actuator there. Okay, So the sensor will tell the controller, the system, that the temperature is not yet 24. Okay, because of due to the open windows. Okay, so the temperature is not 24 degrees Celsius. Okay, so if it fit to the controller, it will compare to the input. Okay, so the controller will know what to do. Okay, so if it's not reaching yet, meaning the temperature is higher, 28 degrees Celsius, so it will tell the compressor to increase the compressor speed, meaning to do more work. Okay, all right. So due to that, a closed loop control system will be insensitive to disturbance due to the feedback. All right. Okay, number 3, normally the control system for the open loop is based on time. Okay, we control if it is on and off system, we just control it based on time. Okay, let's on this for 2 minutes. Okay, for example, on the toaster, you have a setting 1, 2, or 3. Okay, so it's based on time. Okay, 1 is 1 minute, 2 is 2 minutes, and 3 is 4 minutes. Okay, so we just turn the heater for 1 minute, 2 minutes, or 3 minutes. Okay, so the controller is using a time-based controller. While for the closed loop, the controller will be using the error, which is the difference between the input and the actual output. Okay, if the error is positive, then it will increase the effort to the system. Okay, if the error is negative, okay, meaning if the error is negative, and then we reduce the effort to the system. Okay, for example, like aircon system, if the temperature is 28, then it will ask the compressor to work more. Okay, but if the temperature is 18, okay, then it will reduce the control signal to the compressor, to the motor of the compressor. Okay, so it will based on the error. Okay, last one is this is the advantage of open loop system. Okay, the system is stable. Okay, normally this because the system, we design the system and we calibrate the system. Okay, so an open loop system normally has a stable system. Okay, what do you mean by stable system? Okay, stable system meaning the system will be able to provide you the output within a limit, meaning there is a limit to the output of the system. Okay, it will not go beyond the limit. Okay, so if that is the behavior of the system, so we call that the system is stable. Okay, if the system is unstable, okay, we apply the input to the system. Okay, then the output go beyond the limits. Okay, for example, for aircon system, you can set until 30 degrees Celsius. Okay, but somehow due to the instability of the system, the output of the system is actually 40 degrees Celsius. Okay, so that kind of behavior is called as an unstable system. Okay, so for open loop system, normally the system is stable because we design it and we calibrate it. Okay, but for a closed loop system, okay, normally stability, normally you can see stability issues. Okay, this is because we add another component to a system that is already stable. Okay, for example, you have an aircon system. The aircon system is already stable, but then because you want to have a automatic control system, okay, then you add another actuator, you add a sensor there, you add another controller. Okay, then when you put that system together, you have to check whether the system now is stable or not. Okay, because before you add another component, the system is already stable, but when you're adding motor, you're adding controller, you're adding sensor, your system may become unstable. So that's why we need to do stability analysis, which is I said in chapter 4, I think. Okay, stability analysis. All right, so this is the comparison for the open loop and closed loop system. All right, so in control system, we're going to focus on the closed loop system. Okay, by using closed loop control system, we allow the system to be autonomous, meaning automatically controlled. Okay, that's why you came with the term intelligent control, automatic control. Okay, this is due to the closed loop control system. Okay, so we are more interested to closed loop control system compared to the open loop control system. Okay, so the control strategy that you're going to learn, the analysis, the mathematical modeling, most of it is for the closed loop control system, right? So from the first slide, I said that first we need to understand the system. Okay, we need to understand the flow. We need to know what are the components that are in the system. Okay, so in this slide, it shows you all the things that we're going to use in a closed loop control system, right? Okay, first, this is a block diagram. Okay, this is an example of block diagram. Okay, so we represent a system or a device, okay, by a block. Okay, and one block we receive one input and provide one output. Okay, even though I said there is many more, but for you, for a basic concept, we learn we need to understand the CISO system first. All right. So here, the system is actually the one function in a car. Okay, so that function allow you to control the course of your car, meaning whether your car will go straight to the left or to the right. So that's why it is a one process, one function in the automobile system. So we know a car will have more than one function. All right, so it is the process is to control the course of the car, right? So the actuator is the steering mechanism. Okay, so you'll be able to control to the left or to the right by turning the steering of the car, right? All right, so in terms of controller here, because this is just a manual control because it said man, so the controller is a man itself, okay, the driver, right? And then in a closed loop system, we have a sensor, okay? So a sensor, we need to compare between the desired cost with the actual cost, okay? So in this case, the actual is the driver itself, which is the eyes and also the tactile strategy of the driver itself. Okay, so the driver will be able to react based on his eyes by looking to the road. The driver will be able to control to the left, to the right, or just keep forward. Okay. Right, so by looking at this block diagram, we will understand the flow. Okay, so the desired cost. The desired cost is actually, there is a road. For example, there is a straight road. Okay, so that is the desired cost. Okay, so then the controller, the automobile will start, go forward. So the driver will keep looking at the road to compare whether the car is actually following the road or not. Okay, so that is what the function of the driver here. Okay, based on the sensor, his eyes. Okay, based on the feedback, so it will be able to react, and then the reaction is actually the movement of the steering car. Okay. He will be controlling the steering. So the car will go straight or left or right based on the steering mechanism. Okay. Okay, so this is just the definition for the block diagram just now. Okay, so right. There is one more example. Okay. Okay, can anyone tell me what is actually the process here? By looking at this diagram, can you identify what is actually the process here? Muhammad Badrul. If you don't want to answer by voice, you can chat. You can type on chat. Okay, look on the system. Okay, try to understand the process. Anyone? Muhammad Azman. Tayo Wen.
Oh, betul.
Mama Hazman pun boleh.
Is the process emptying the barrel?
Emptying the barrel. Okay, all right. Any other idea? Firdaus Fauzi? Muhammad Wafi Irfan? Wafi Irfan? Ada tak ada ni korang ni? Tu saya cakap seorang-seorang je. How about Tariq Daud? Okay, if I don't call your name, you can just type your answer on the chat there. What do you think the process is? Okay, yes, it can be emptying the water from the container, but we can also yes, Ayuni, control the water level. Okay, so we need to make sure that the water level in this tank is always at the set level. Okay. Okay, let's say you set the water level in this tank is 5 meter. Okay, so the input will keep flowing in. Okay, the fluid input will keep flowing in. All right. So the job of the man here is to control the opening of output valve. Right? Yes, that is correct. Ikhwan. Right? Faiz Yaakob. Yes. Okay, so the job of the man here is to control the flow of the output fluid so that it will be able to maintain 5 meter. Okay, so what happens if the water level is 3 meter? What happens if the water level is 3 meter? What the man need to do?
Close the valve.
Okay, close the valve. Yes, correct. Okay, you need to close the valve so that the input liquid will fill up to the 5 meter again. Right? So if the level is 6 meter,
open back the valve to exact amount 5 meter back.
Yes, you need to open more opening, maybe more or open more widely. Okay, as compared to 3 meter, 4 meter. He may need to open some of the valve, meaning there is some opening of the valve. Okay, but if the water level is more than 5 meter, you need to make sure that the opening is closed or a smaller opening only. Okay, so this is example of controlling a water level system, right? So we can see okay, so the input is the reference fluid, okay, the setting reference fluid. The output is current level of fluid, okay, the current level. Okay, the controller is the man, okay, the operator. The actuator is the valve. Okay, you can open and close the valve, and the process is the valve handle. Okay, the process is actually it's not the valve handle. That is the actuator process, which is opening and close the valve using the valve handle. But the process is actually the relationship between the flow in and flow out. Okay, the water level system. Okay. All right. So the roles of controller engineer, you need to be able to identify the components. So you need to make sure that what is the appropriate actuator to your system. Okay, what type of controller, what type of sensor. Okay, you need to identify that. Okay, second, you need to be able to design a controller. Okay, whether to use PID controller, whether to use more advanced controller like adaptive controller, model predictive controller, or just using a simple leak-led controller. Okay, so you need to be able to identify a suitable type of controller. Okay, and then able to model, to come out with mathematical model for your system. Okay, for your closed loop system, what will be the mathematical model? Okay, so that we'll be able to simulate the behavior instead of developing the prototype of the system, the tank system, in order to control that. Why not we just come out with a mathematical model, then we simulate the behavior in the software. Okay, and then of course you need to able to come out with the block diagram. Okay, and then to do the analysis in terms of time response, frequency response, and stability analysis, and then able to simulate the behavior of the system. Okay, so basically this is what we're going to cover in this course. Okay, first we will start with block diagram and mathematical model. Okay, this will be covered in the next chapter number 2. All right, so this is one example of case study for the turntable speed control. Okay, so we're going to control the speed of the turntable. So what is the turntable? Turntable is actually the application normally found in CD, hard disk drive. Okay, where we have a motor and a turntable. So you put a CD there, so the motor will rotate so that you'll be able to read the data on the CD or hard disk. All right. So the objective is to design a system for the turntable speed control to ensure speed of rotating lies in certain range. Okay, you want to control the speed of the turntable. All right. Let's see the open loop system first. Okay. Before you control before you design the closed loop system, of course, there is already an open loop system. Where in this open loop system, the controller is just setting speed. Okay, because the turntable system use a DC motor as a actuator. So the input to the DC motor is voltage. Okay, so we know that for the speed of motor, it will depend on the voltage. If you provide low voltage, it will give you low speed. If you provide higher voltage, the motor will rotate at higher speed. Okay, so you can see the speed setting, meaning you set the voltage to the motor. Okay, so maybe the first setting is 1 volt, second setting is 3 volt, and the last setting, the maximum setting is 5 volt. Okay, so then we have a DC amplifier here, which act as a controller there. So the function is just to amplify the voltage to the DC motor. Maybe the DC motor require more than 5 volt or more than 3 volt. So it will amplify the signal. Sorry, again, I have a disturbance here. Okay, sorry. Alright, so this is the open loop system. So you can see from the block diagram, it is just on-off system, okay, which is open loop. There is no feedback there. Okay, so when there is no feedback, we don't know the actual speed of the turntable. Okay, we only supply the voltage to the DC motor. Let's say we already calibrate 5 volt, we provide you 100 RPM. Okay, that is the calibration for the motor. Okay, 1 volt we provide you 40 RPM, 3 volt we provide you 80 RPM, and 5 volt we provide you 100 RPM. Okay, but the whole system is a combination of DC motor and also turntable there. Okay, meaning there is additional weight to the DC motor. Okay, your calibration is without weight. Okay, so your actual output may not as the calibration one. Okay, you set 5 volt, but due to the turntable weight, then there is another component there. There is a friction maybe. Okay, so the RPM, the DC, the turntable will not rotate at 100 RPM. Okay, so the system will not know the actual speed of the turntable because there is no feedback. Okay, so now we want to design a closed loop control system. Okay, closed loop control system, which allow us to control the speed of the turntable so that it will lies at certain range. Okay, so the additional component that you can see here is the tachometer. Okay, the additional component here is the tachometer, which is the what we call that? Which is the sensors, speed sensor. Okay, so we use tachometer to measure what is the actual speed of the DC motor. Okay, so that the system, okay, the controller will be able to increase or decrease the voltage to the DC motor due to the error between the actual speed and the setting speed from setting, right? So in terms of block diagram, okay, so the block diagram for this turntable speed, speed control, okay. So we represent the process as the turntable disk. Okay, the actuator is motor, the sensor is tachometer, and the controller is amplifier. Okay, so you can see this is the closed loop block diagram because there is a feedback from the output to the input using a sensor there. Right. Right. More example here. Liquid level system again is the same like just now. Instead, but the difference is now we are controlling the input flow. Okay, this is a flushing tank. Okay, so instead of controlling the output liquid, now we are controlling the input liquid. Okay, so it's still to maintain the level, the water level in the tank. Okay, so the float here is the sensor. Okay, and the controller here is the mechanism in the mechanism here that will allow the system to control the opening of the valve. Okay, so the mechanism between the float and the valve. Okay, there is one mechanism there that allow meaning based on the height of the water due to the float, it will be able to control the opening of the valve. Okay, then we have a robot control system. Okay, robot control system where for this example, the robotic arm here will need to pick up something here, device maybe, a workpiece maybe, okay, pick up and then put onto the work machine. Okay, so for this system, the sensor is the camera. Okay, the camera. Okay, so the camera will feed the signal to the controller. Okay, and then the controller will control the robot arm. Okay, what do you think the process is? What do you think the process is? Meaning based on the feedback, the sensor here, this camera. Okay. Anyone has idea? Okay, it may the process may it may due to the trajectory of the controlling the trajectory of the robotic arm. Okay, in order to avoid obstacle, maybe there is an obstacle here or here, so the camera will tell the controller if there is any obstacle there, so the controller will able to plan the trajectory of the robotic arm. Okay, in order to pick the workpiece and put into the work machine. All right, last one is the temperature control system. Okay, we have a heater. Okay, the heater is the process there, heater in the furnace. Okay, the actuator is the relay. Okay, the actuator is relay. The sensor is a thermometer. Okay, and then the controller will be designed in this PC-based system. Okay, in the PC. Okay, so user we provide input to the controller system. Okay, here you can see that for a closed loop system, the system will become more complex. Okay, so for example here, because the thermometer here is analog sensor, okay, analog type of sensor, but your controller is in PC. The computer only understand the digital signal, so therefore we need to convert from analog signal provided by the thermometer using analog to digital converter. Okay, so that the controller will be able to understand. Okay, for example, the temperature is 24 degrees Celsius. Okay, but the computer doesn't understand 24 degrees Celsius. We will need to convert that 24 degrees Celsius to a digital signal. Okay, so after conversion, 24 degrees Celsius may be converted to 11001110. Okay, it's a binary signal. Okay, same goes to the actuator here. Since the actuator will only receive an analog signal, but the control signal calculated in the software is in terms of digital. So we need to convert that. Okay, but here, okay, let me see. Because in this example here, there is no digital to analog converter. Okay, so I believe the relay here is only on-off relay. So meaning it receives a digital signal because it is on-off. So that's why we don't have any analog to digital to analog converter here. Okay, so it will depend on the type of actuator and also the type of sensor. Analog sensor, digital sensor. Okay, you will learn about this in instrumentation. Okay, last one is line following robot. Okay, the difference between line following robot and the temperature control system or this robot control system is the controller, the type of controller that used in that system. Okay, so this is what we call as PC-based controller because the controller is in PC. Okay, we design the controller in a computer, in the PC. So we call that as a PC-based controller. Okay, while for this one, the controller is is actually embedded in the mobile robot. Okay, so you can see that the controller is very small because we use a microcontroller there. Okay, it still consists of sensor, actuator, system, all it is embedded in one system. Okay, so the difference here is the controller type. So for mobile robot, for any mobile application, normally we use a microcontroller type of controller, or normally microcontroller lah. Okay, other than that, we also have PLC, which is normally used, for example, in industry. Okay, this one may use PLC controller, okay, in order to control the movement of the robot. Okay, so in terms of controller, we have 3 types: PLC based, PC based, and also microcontroller based. All right. I think we stop for 5 minutes before we continue with mathematical modeling, chapter number 2, right? Principal method. Okay, I already mentioned about first principle method, where I said that we're going to learn about the basic equation of the elements of the system. And then from there, we can draw a block diagram. Okay, and after block diagram, we'll be able to manipulate it or to get the final transfer function of the system. Okay, so I believe there is, okay, the system that we're going to learn in this chapter, the first one is mechanical transitional system, right? And then we're also going to see on mechanical rotational system, still mechanical system, but in terms of rotational system. Okay, then we have additional component for that, lever system and also gear system. Okay, then we have hydraulic system. Okay, then liquid level system. Okay, the water tank system just now. Okay, then we have a thermal system and also electrical system. Okay, there are the system that we're going to see, meaning we're going to see what are the elements in mechanical transitional system, mechanical rotational system, and what are the equation. Okay, and then at the same time, we're also going to learn on how to draw a block diagram. Okay, so first, the first system is mechanical transitional system. Okay, in mechanical transitional system, we only have 3 elements. Okay, the first one is spring, the second one is damper, and the third one is mass. Okay, only these 3 elements. So you may find a system that consists of spring, mass, damper, spring system, 2 spring, 2 mass, 2 damper. Okay. Example of a system that we represent using a spring mass system is a suspension system. Okay, suspension system for a car. Okay, normally we represent, we model the system, the car as a mass, and then there is a spring and also there is a damper there. So from there, we'll be able to model and then get the mathematical model, and then we're able to simulate the behavior of a suspension system. Right, so it all based on these 3 basic elements. Okay, the first one is spring. Okay, I believe everyone know the equation for spring. Okay, what is the equation for spring? Anyone? Okay, yes, Zuhai, Muhammad Azman, F equal to Kx. Okay, so we have F equal to Kx. Okay, So we know F is force for the spring force. Okay. K is the spring stiffness coefficient. Okay. And X is the displacement. Okay. So that is a very basic equation, right? F equal to Kx. Everyone know this. Okay. For the spring, we have two conditions. Okay. For the first one here, okay, you can see that one end of the spring is fixed. Okay, there's a wall there, fixed. Okay, and on the other end, okay, the spring will displace by X displacement. Okay, so therefore the equation is Fs equal to Kx because the displacement is only at one end. Okay, for the second scenario, okay, for the second scenario here, you can see that both end, dua-dua hujung dia has a displacement. Okay, both end has a displacement. Okay, so one end has xi, which is normally I is known as displacement input, and then O or not is what we call as output. Okay, so but the important thing here is that both end has a displacement. Okay, one end with xi, another end with x naught. Okay, therefore the equation for this scenario will become Fs equal to K xi minus x naught. Okay, so normally we write xi minus x naught because our assumption, we always assume that xi is bigger than x naught. Okay, this is just assumption. Okay, so because I want to write xi minus x naught, that's why I assume xi is bigger than x naught. So the calculation will be positive. Okay, but if you assume x naught bigger than xi, then you need to write x naught minus xi. Okay, it's just a notation actually, but in order to simplify the process, we just assume xi is bigger than x naught. Okay, so the equation will become K xi minus x naught multiplied with xi minus x naught. Okay, so two scenario for the spring. F equal to Kx or Fs equal to Ksi or minus x naught. Right, so that is the first element. The second element. Okay, the second element is damper. Okay, the second element is damper. The equation will become, so you can see there is also two conditions here. This is the first one, this is the second one. Okay, so for the first one, force for damper is equal to CV. So V here is velocity. Okay, damping coefficient, C is damping, viscous damping coefficient, multiply with the velocity. So you provide the force. Okay, but we want to have an equation that contain X in there. X is the displacement. Okay, you can see this is X there. Okay, so the relationship between velocity and displacement is, we know that V is also equal to dx per dt. Right? We differentiate displacement, we get the velocity. We double differentiate displacement, we get acceleration. Okay, that is basic relationship. Right? So we can simplify this to become equal to dx. Okay, why I write d? Because d here is what we call as d operational, which is equivalent to d over dt. Okay. You can see here, this is d over dt. Okay, it's just to simplify the way of writing that. So we, because when we're going to draw a block diagram, if you put d over dt, then it will crowd. The block will become crowded. Okay, so we simplify that. We just say, okay, this capital D is d operational. It represents d over dt. Okay, so the equation here will become FD equal to CDX. Right? So this condition is true when only one end of the damper has a displacement while another end is fixed. Okay? So saying that, therefore, for the second condition, where you can see both end has a displacement, okay? One end has xi displacement, another end has a x naught displacement. So the equation will become FD, F damper equal to CD xi minus x naught. Okay, same like the spring just now. Okay, so the equation for damper is CDX, and the equation will be different. Is both end has both displacement. All right, the last one is the mesh system. Okay, last one is mesh system. Okay, the equation for mesh system is normally we write F. Okay. F equal to MA. Okay, mass multiply with acceleration will give you force. Okay, and then again we want to have the equation in terms of x, so we will write F equal to m d square x. Okay, d square meaning d over dt square. Okay, so that is the equation for mass. All right. All right. So now we know the basic equation for a spring mass system. Okay, we know equation for spring. We know the equation for damper. We also know the equation for the mass. All right. So now, how to draw a block diagram if there is a combination of this. All right. Okay, let's do example number 1. Okay, example number 1. So here you can see in this example, we have a combination of spring and mass. Okay, we can see that, okay, there is one spring attached to the mesh here, attached to the mesh here. Okay, okay, and then the mesh will displace. Okay, so the first step is actually to determine what is the input to the system and what is the output to the system. Okay, meaning what is the input, what type of input we apply to the system, and what are the output that we want to see from the system. Okay, so from the statement here, it's already mentioned that xi is the input and x naught here as the output. Okay, so the input is xi and the output is x naught. Okay, of course we need to understand, we need to know what is the input and output to the system. Okay, this is a very first step in drawing a block diagram. We need to know what is the input and what is the output. Okay. All right. So next, okay. The second step is to do a free body diagram. Okay. we need to do analysis on this system. The analysis that we can do is analysis on the force on the body. Okay, so we're going to do a free body diagram on the mass here. Okay, so from the system, we see there is only one force that will be acting on the mass. Okay, that is due to the spring. Okay, because when we apply input displacement to the spring, okay, it will produce a force and it will move the card. Okay, so we draw here. This is Fs. Okay, force of the spring, and we know that it will equal to Ma. Okay, the mass will have an acceleration there due to the force. Okay, okay. Now we need to determine what the direction of the force, whether it will pull the mass to the left or push the mass to the right. Okay, so in order to analyze the direction, let us just consider the spring here. Okay, let's just consider the spring there. Okay, so our assumption, okay, we always consider that xi is bigger than x naught. We assume xi is bigger than x naught. Okay, so if xi is bigger than x naught, what do you think the state of the spring? Is the spring is in tension or the spring is in compression? Okay, if xi is bigger than x naught, okay, is it tension or compression? Anyone? Zuhai, compression. Muhammad Azman, compression. Nafizan, compression. Yes, that is correct. Okay, so the state of the spring now is in compression. Okay, so we said that the spring is in compression. Okay, what will be the reaction? Imagine yourself, someone compress you. What will be your reaction? Okay, you will try to push back, right? Okay, someone push you, so you will try to push back. Okay, so the reaction will be okay, so this one will be the reaction. Okay, so the spring will try to push back. Okay, so therefore here, okay, this is the direction, right? So the spring will push the card to the right, right? So from there we will write the equation for the mass. We said that Fs, force of the spring, will equal to md square x. So this is our first equation. All right. Then we will write all the equation for other elements, which is the spring, because we only have spring here. So we also write the second equation, Fs equal to k xi minus x naught, because both end of the spring will have a displacement. So the equation will become k xi minus x naught. All right. So that's all the equation in this system. Okay. So once we have these two equations, now we can draw a block diagram. Right. So in order to draw a block diagram, okay, before we draw a block diagram, any question from you guys regarding free body diagram, regarding the equation or etc.? Anyone?
So far good, Doctor.
Okay. Okay, thank you, Taufik. All right. Thank you, Hafizan. All right. Okay, so now let's continue with drawing a block diagram. Okay, so we will start to draw a block diagram. Start from the output. Okay, so we already know that the output is S naught there. Okay, S naught is the output. So we will draw an arrow for the output. So draw an arrow for S naught. Okay. Meaning now we're going to find what is, okay, I believe the equation will be here S naught, right? Okay. Okay, so we need to find what is the equation for S naught. Okay, so in this example, we have two equations and both of the equation contain S naught term. Okay, dua-dua ada S naught kan, dalam equation satu ada S naught, equation 2 pun ada S naught. Okay, so meaning we can choose any of the equation. You can start with equation number 1. You also can start with equation number 2. Okay, but remember, one equation can only be used once. Okay, satu equation tu boleh guna sekali je. Kalau dah guna, lepas tu dah tak boleh pakai lah. One equation can only be used once. Okay, which one do you want to start? Which equation? Pilih.
1.
Okay, Taufik want to start with equation number 1. Okay, let's draw based on equation number 1. Okay, first we need to rewrite equation. Okay, so from equation 1, okay, we need to rewrite so that the equation will become in terms of the output, which is our S naught, output equal to something. So we rewrite from equation number 1. So the equation will become S naught equal to 1 over md square multiply with Fs. Okay. So if you notice here, okay, this is S naught is what? Okay, S naught is variable. So in this case is output variable. Okay, because it is on the left side, so it is output. Here is constant. And then here is the input variable. Okay. So this is the form of the equation. Output equal to constant multiply with the input variable. So meaning when we write S naught equal to 1 over md square multiply by Fs, so S naught will become the output. That's why we draw the output arrow here. Okay, because it is the output. Okay, then the constant will be in the block. Okay, 1 over md square. Okay, and then Fs is the input arrow. Fs. Okay. Okay. All right. So that is the form for what we call as a multiplication equation. Okay, because the operation of this equation is multiply. 1 over md multiply with Fs. So we call this is a multiplication equation or division equation. Okay, so the form will be in terms of a block, one input arrow and one output arrow. So output arrow will be output variable and input arrow will represent the input variable. Okay. All right. Okay, next. Okay, so we have draw a block diagram for equation number 1. Okay, next we need to solve for Fs. Okay, because your now Fs has become the arrow, the output arrow. Okay, kat sini saya tak boleh move apa. So saya draw kat bawah lah. Saya draw lagi sekali kat sini lah. Okay, so this is x naught 1 over md square and the input is Fs. Alright, so we need to solve for Fs. So in order to solve for Fs, we need to find what is the equation that contain Fs. Okay, so since we already use equation number 1, because both equation contain Fs. Equation 1 also contain Fs. Equation 2 also contain Fs. But since we already use equation number 1 to solve for x naught, then we only have equation number 2 now. Okay, so for equation number 2, okay, so let's see what is the operation for this equation. It's already in terms of Fs is the output, then there is a constant and input there. Okay, so we don't need to rewrite the equation. Okay, what is the operation there? Okay, it is a multiplication, right? K multiply with xi minus x naught. Okay, so therefore, again, we're going to draw a block with input arrow to it. Okay, so Fs equal to K, so K will be in the block because K is constant, while xi minus x naught is variable. So the input will be xi minus x naught. Okay, now we need to solve for xi minus x naught. Okay, so here we don't have any equation because it's just an operation there. So xi minus x naught is a minus operation or add operation, but this one is minus operation. So if you see the term that contain minus or plus sign, minus operation or plus operation, then you're going to draw a summation point. Okay, this is what we call as summation point. Okay, so the characteristic for summation point. Okay, the summation point can receive many input. Okay, meaning you can draw 2 input, 3 input arrow, 5 input arrow to it, but it only has 1 output. Okay, you can only draw 1 output arrow from a summation point. Okay, we already have the output arrow xi minus x naught, meaning this summation point will receive 2 arrows. Okay, we receive 2 arrows. Okay, so let's put here xi. I choose xi because xi is the input to the system. Okay, the sign is plus because here is plus, right? Okay, and then for the x naught here, the sign is minus. Okay, it's just a sign there. Okay, plus and sign. So from there we'll be able to read the summation point. It will produce xi minus x naught based on the sign. Okay, if I put plus sign here, so meaning the output will become xi plus x naught. So it depends on the sign that you put on the summation arrow, summation point. Okay, so now we're going to solve for x naught. Okay, we just leave xi there because xi is the input to the system. Okay, so input to the system, there should be no anything, meaning kita tinggal je macam tu, input arrow, so input to the system. Okay, but for x naught, it's not the input to the system, we need to solve that. But since we already have x naught here, you can see that there's already x naught there. Okay, so therefore we don't need to find any equation that explain about x naught. Okay, because x naught is already there, we already defined x naught, so we just tap from here and then fit to here. Okay, so meaning we said, okay, xi minus s naught, so s naught is from the output here. Okay, from the output here. We feed to here. Right? Okay, so this is the complete block diagram for a spring mesh system. Yeah, for this spring mesh system. Okay, so I hope you can see the step of how we can draw a block diagram. Okay, using first principle method. Okay, we write the equation, the basic equation for the system using first principle method. We analyze using free body diagram. Okay, if more components, then you need to do more analysis on that. Okay, then we list all the equations for all the elements there. Okay, then from there we start to draw a block diagram based on the equation. Okay, so you need to know, is this a multiplication equation or this is a plus or add equation? Okay, if it is a multiplication equation, then you will draw a block there. Block one arrow in, one arrow out. Okay, if the equation contain plus or sign operation, then you will draw a summation point. Okay, so that's all for the block diagram. It just contains block and summation point. Okay, but we need to determine the relationship between all the variables in the system. Okay, I think I will stop here. Okay, I will open to the question.
Doktor, sorry, boleh minta ulang balik tak kenapa anak panah X naught tu dia sambungkan?
Okay, boleh. Alright. So, macam mana nak cakap? Okay, for example, just now when we finish draw the first block diagram here. Okay, when we finish draw the first block diagram, the next step will be to ask yourself what will be the equation for Fs. Right, so you find on your list of equation, you will find which equation does contain Fs. Then you can use the equation. If you need to rewrite the equation, you need to rewrite, or don't, you just draw it. You just use the equation and then check whether it's multiplication or summation. Okay, for the last term here, okay, where the input arrow for the K block is xi minus x naught. Okay, so when we see xi minus x naught, then there is no other equation. Okay, so we just need to see the operation. So since the operation is minus operation, okay, so we draw a summation point. Okay, so we draw a summation point there. From the equation we know there will be two input arrow. Okay, the first one is xi, the second one is s naught. Okay, I already explained about xi. Xi is the input to the system. Okay, but x naught, in order to solve x naught, again you need to ask what is the equation that solve for x naught. Okay, all right, so you will ask that question. But then you realize all the equation is already used. You only have two equations, equation 1 and equation 2, but both has been used. Okay, meaning we cannot use the equation anymore. Okay, we cannot use the equation anymore. Okay, so then if that is the case, try to find from the block diagram whether the block diagram is already contained your variable just now. So in this case, it is s naught. Okay, since s naught is already defined from equation number 1, okay, which is the first term, the first here. Okay, so because it's already there, we just can use that. Okay, so meaning the signal here is represent s naught. Okay, the arrow here represent s naught. So we just can tap saying this is s naught, and then we bring it to the summation point here, telling the system that this signal is s naught. Okay, because the variable, the term is already in there. It's already defined. So we just can tap. We can just use that. Okay. Later on, you can see, for example, sometimes you have another equation. Let's say another equation. Let's say there is FD equal to CD XI minus S naught. Okay. So you can see the term XI minus S naught is already in this equation. You can see there is already SI minus S naught there. Okay. So for that reason, you can just tap later on. Okay. Tap from there, then multiply with CD, give you FD. Okay. There is another example. Tapping the information that is already in the block diagram. Okay, I delete this. Okay. Boleh faham tak?
Boleh.
Okay. Lagi? Ada soalan lagi tak?
Doktor,
Yes, Zuhair.
ya, saya nak tanya, dia yang for the arrow from XO to the summation point tu, dia tak kisah in what direction we do, whether it up or down, it doesn't matter.
Tak kisah. Okay. Kalau you nak draw dari sini ke sini pun boleh juga.
Okay.
Maksudnya kata, okay, this is S note kat bawah. Boleh je kat bawah. It doesn't matter. Okay. Apa lagi nak cakap? Apa ni? Okay. Okay, so a good practice in drawing a block diagram, we always try to draw the input. Okay, this is the input, right? The input XI. It is in line with the output. You can see my drawing is in line. Okay, meaning satu garis lah, satu garis. XI satu garis dengan S note. Okay, XI, the input is in line, in one line, connected to the output S note. It's a good practice. Okay, so therefore you can determine, okay, this is the feed forward line because it feed from input straight to the output. We call that as feed forward line. Okay, and then as for this one here, we call that as the feedback line. Okay, so it is a good practice. I'm not saying that if you draw XI here, then, for example, you draw XI here, then you have block, then you have X note here, maybe you have another summation point and etc. Okay, it's not wrong actually. Okay, you can draw like that, but later on when you're going to do a block diagram manipulation, you're going to do a signal flow graph. If you draw XI in line with the S note, it will be easier for you to determine which is feedback, which is feed forward. Okay, easier for you to draw the signal flow graph. Okay, so it is a good practice. Okay, kadang-kadang kalau kita tak ada ruang, terpaksalah juga kita lukis mana-mana kan. Tapi itulah, it's a good practice to have input in line with to the output. Alright. I think so far it is this is the only thing that I'm going to explain to you for today. For Thursday, right? Thursday 12, right? 12 or 11 our class on Thursday?
12.
Okay. So Thursday 12, we're going to do more example on how to draw a block diagram. Okay. Kalau kita start dengan equation 2, oh yes. Okay. Let me show you. If you have class, you want to leave, you can leave. I just want to show if we start with equation number 2. Okay. Basically, you can see that by using equation number 1, or having said that, it doesn't matter equation number 1 or number 2, but actually if you start with the equation that contain md square here, that contain this term md square, okay, the main equation, which is the summation force to the mass system. Okay, if you start with that equation, your block diagram will become more simple. So you can see it's quite simple to draw this block diagram. Okay, let me show you the block diagram if we draw using second equation. Apa gelap pula ni? Macam mana nak tukar? Macam mana nak tukar? Okay. Okay, so we start with equation number 2. Okay, so we still need to rewrite equation number 2. So we write from 2, x naught will equal to fs2 divided by k. Is it plus or minus? Equation tadi. That fs2 pula, fs je. Fs equal to k xi minus x naught. Okay, so then k to here. Okay, so the equation will become xi minus fs divided by k. Okay, so that will be the equation. Okay, so from this equation, we can see that the operation is minus operation. Okay, so meaning we're going to draw a summation point. So let's draw a summation point. Okay, we know the output is the x naught, and there will be 2 input, which is xi, and then there is a term of fs divided by k. Okay, so you can see the block is quite complex. Macam mana saya nak tarikkan sikit. Okay. Alright. So since xi is the input to the system, okay, we just leave it there. And then we need to solve for fs over k. Okay. So fs over k is a multiplication operation. Okay, because there is no equation that contain fs over k. So so we're going to draw arah mana sesuai. Okay. 1 over k, then this is fs. Okay. So from equation number 1, okay, equation number 1, let me write again. Equation number 1 is fs is equal to md square x. Okay, so kita balik padam balik ni sebab x md x square x not right. It's not. Okay, so saya patah balik ke sini. Mana pemadam ni? Okay. Okay, saya lukis kat sini. Okay, so here is 1 over k. So meaning the input to the arrow is fs. Alright. So from equation number 1, fs is md square multiplied with x naught. So it will be md square And the input is X node here. Okay, so this is X node. Okay, sorry. Right. So basically that will be the block diagram. Okay, so it will be quite confusing if you don't have meaning kalau you tak biasa lukis block diagram, nanti you akan confused lah. So that's why my tip is to start with equation that contain MD square, meaning the main equation for the system. Because later on you will have, if you have 3 or 4 components that add onto one mass, so you have a summation of force acting to that mass. Okay, so always start with the equation. Okay, all right, so I think I stop here. Okay, we will meet again on Thursday, 12, with more example on how to draw a block diagram. Okay, so thank you. Assalamualaikum warahmatullahi wabarakatuh. Attendance, I already take the attendance automatically. Okay. Basically, I believe already is captured here. I will share the file so you can check whether your attendance is captured or not. But I believe it's already captured here. Okay, thank you.